In the last class, we started with stochastic subgradient descent. So this is basically a stochastic gradient descent, but for non-smooth functions. And we defined what is stochastic function. So we are doing this from the notes. Stochastic subgradient descent, and we defined a stochastic function, and so we are given a function f from Rd to R, and we can write this as fx equals to Ed and f xi of x. So we are basically defining a stochastic function. So what do we mean by stochastic function? So basically this function is given as a expectation of some random variable, and here d is some distribution over Rq. Xi is a random variable from Rq, and it is sampled from the distribution D, and Fji is from Rd to R. So this is the meaning of a stochastic function. This has some randomness basically. So it depends not only on x, but also it depends on a random variable xi. So we have done this, and then we also recall from the last class that we wrote down some assumptions, and these assumptions were, let us say, first one is convexity. So this means for every xi in Rq is convex. Okay, so we are trying to extend the definition of convexity now. So what it means for a stochastic function to be convex. So a stochastic function is convex when it is convex for every possible choice of the random variable xi. So, and then what we assume is that although this function is stochastic, it will have the proper subgradients whenever we need it for whatever xi it is. Okay, so it should not be the case that for certain random variable xi, I'm not able to compute the subgradient at a point x. Okay, so we want to have this consistency. So for any given choice of xi, I am okay to calculate a subgradient for any given x. So that's the guarantee we want. So subgradient selection. So this means that there exists a function g from Rd cross Rq to Rd such that for every x xi pair, so in the stochastic function, it's not just the domain of the function x, but also the random variable now. So that's why we talk about x and xi. In R d Rq, we have the existence of a subgradient x xi g x j in subdifferential f j x. Okay. So basically this guarantees that there will be a subgradient for every choice of the random variable and the domain point x. There will exist some subgradient. Okay. And then all this is needed for the algorithm. Okay. So then another thing is bounded subgradients. So this means, as the name suggests, bounded means that the subgradients will be bounded. Okay. So they should not like go to infinity and so on. So there exist g greater than 0 such that for all x in R D, expectation of g x j whole squared is less than equal to g squared. Okay, so that's what it means that the gradients are bounded. So these are the assumptions we have, and then so SSD, so stochastic subgradient descent. So here let us assume these things that, so consider the problem is stochastic in the first place. So the function that we are minimizing is a stochastic function, and assume that we have stochastic convexity and g bounded gradients. So let us choose an initial point x naught in RD, and let gamma t greater than 0 be a sequence of step sizes then we define this algorithm chi t in R Q, and this is sampled I D, chi t comes from the distribution, and then x t plus 1 is x t minus gamma t g x t chi t, where g x t chi t is in the subdifferential of del f chi t x t. So this is a stochastic subgradient descent method. It's stochastic because the function we are minimizing is a stochastic function now. So it's a random variable now, and the randomness is determined by the chi, and it is a subgradient method because we don't assume that the given function f is smooth, or meaning differentiable. So hence it's a stochastic subgradient descent method. So where does this arise in machine learning? Let us say, so I have the loss function calculated over the features and the labels y, then this could be written as small loss functions li xi yi, I equal 1 to m are the number of samples. So I can define them like that. So this could be our f, small f. Okay, so if you want to use the notations from the optimization literature, then we can take this as a small f, and these are the fi's. Okay, so So in this, like in machine learning, okay, how does these things fit in machine learning? So that's what I'm trying to explain here. So f is sum of these fi, and then if what happens is that I'm supposed to compute the gradients at a certain point. Let us say, I mean, since this will be a function of some parameter theta, okay. So the way to see this is that xy's are there in the error calculation, but I see this as a function of theta. So theta I plus 1, and here, I mean, I should not say I plus 1, it's just the variable I theta, and here there is a theta here as well. So this is what machine learning losses are, where you are trying to minimize the loss over some theta. Theta is the parameter of your model, and this is these losses are computed over each sample, I equals 1 to m. Okay, so when we use gradient descent, then we are supposed to compute the gradient at certain point theta. Okay, at certain point theta I, let us say I start from theta 0, and I'm supposed to compute at theta I. Then when I will look for computing the gradient at the point theta I, then I see this very big gradient being to be computed, where because m in machine learning could be several thousands, tens of thousands, or 100,000 or million. It's very common. Okay, so computing the gradient of this sum over these million terms is prohibitive. Okay, so you cannot really spend so much time on that. So that's why people go for so since m can be very large, up to the order of sometimes millions, okay, is very realistic. So hence computing full gradient grad f theta I is very costly. Okay, so that leads us to stochastic, like we have discussed this, right? So that leads to stochastic in the sense that now rather than seeing f as a sum of all the small losses, you treat f as some as sum of some approximations of this sum. So basically you pick only sum of the samples over which the losses are calculated, and those choices of the sample will be random. Okay, so the xi is seen like that here. So xi will be a random sample that I will pick from here. Okay, or if I have to pick xi, I can also see it as a vector of length rq, and then I can say that maybe I have a batch of q examples, then each of these q samples that I will pick, q is less than m obviously, then on a batch of q samples I can pick randomly each of the q. Okay, so in that case it's as if you have a stochastic function which is parameterized by xi. Okay, so this is our stochastic function, and this is parameterized by xi, but we are using xt, but since x is reserved usually for the samples, so here we changed our notation from xt to theta. Okay, or theta I. Okay, so since hence computing the full gradient is costly, so we look for gradients which are cheaper, right? So look for cheaper way to compute. Okay, so cheaper way to compute the gradient, and the cheaper way is, as I said, just on some samples we will approximate the f as a sum of those only on the selected samples. So cheaper way would be compute gradients only on a batch of samples. So let us say in our case the batch of samples are like xi1, xi2, xiq, where q is less than m. Okay, and the xi could be seen as a random variable that picks these indices. So xi here I will see this as a vector of in RD, and this I will see this as a vector IQ, and this is indeed okay. So obviously you will sample these indices, and these ij indices are coming from the index set 1 to m. So this is the notation for the set from containing 1 to m. Okay, so we will pick this randomly. Okay, so hence this xi, since xi will be picked randomly, right? And then our function, let us say I use tilde as a approximation of the function, and this is only on the batch. So this will be f I1, or let us say I k, and k equal 1 to q. Okay, so I have approximated my function f as a sum of fi's, but only on these small samples. But the fact that I choose this ik randomly, which indices I pick, this makes it a stochastic function. Okay, so hence we can say that this is, in our notation we can say this is a xi. Okay, and then in our case, like in machine learning, we use theta or w. So in place of x we can write this as a stochastic function. So this is exactly what we are doing is exactly for solving these problems. Okay, and we are doing one more step where we are saying is that f can be non-smooth. Okay, so in some cases f xi theta can be non-smooth. So if you have seen a little bit of neural networks and stuff like that, then so for example, so using activation functions like ReLU, which is very popular. Okay, and you can consider like any kind of thresholding, sign functions, any kind of nonlinearities we have, I mean non-smoothness. And so basically if you are going to train this, then you are supposed to use this optimizers, right? So this is the context we have in hand, that we have this method for such class of problems, and we want to know whether how well it converges. Okay, so we will try to see. So we will next we will do this proof that stochastic subgradient descent is convergent. Okay, so maybe I can use this because this algorithm is very simple to remember. And one result that we have shown in the last class was, oh no, we didn't show this in the last class, I believe. Yeah, this is not what we showed. We stopped at the stochastic gradient. So this is lemma 9.4. So if assumptions which are stochastic convex and G bounded subgradients okay. So these are the assumptions, stochastic convex and G bounded subgradient. So we have defined this in the previous class. So if this holds, then for all x in Rd, we have expectation of G of x j is in the subdifferential of f. So what is to be noted here is what we know is that G x j is a subdifferential of del f j at x. This is what we know, right? And what we are proving is this. And f j, if you recall, is an approximation of the f. Okay, so f j is basically this, and this is not the full f, but the sum of some randomly selected fi's. So what we are saying is that if this guy f j x, there is a gradient of f j at x, then if I take the average of that, the expectation of that, then on average it is like it is in the subdifferential of f at x. So the expectation of the gradient computed for f j, which is an approximation, is actually in the subdifferential of f at x, which is the original function, not the approximated one. Okay, so in the original function I have the expectation of this. So this is the result we will try to prove. So what we know is that this belongs to the subdifferential of f j. So we use the definition of the subdifferential. So since G x j is in the subdifferential f j x, then by the definition of subdifferential we use that formula, right? Fy minus fx minus eta y minus x must be greater than or equal to 0. Then eta is the subgradient, right? That's how the subgradient is defined. So in place of eta now I will have this. So this is f j y minus f j x minus G x j, and then y minus x is greater than or equal to 0. So this is from the definition of subgradient. Okay, and now we will take expectation. So we have a I here that we will have an expectation of this, and what we are supposed to prove is that if this is in the subdifferential, then what we are claiming is that f y minus f x minus this guy, expectation of G x j comma y minus x, is also greater than or equal to 0. Okay, if that happens, then we immediately claim that this is the subgradient of this. So this looks more or less okay, that the next step should be just take the expectation, and we know that expectation of this guy is the f itself. Expectation of this guy is the f itself. and expectation of this will be this, and there is nothing to do here, and it still remains greater than equal to 0. So taking expectation with respect to xi, and so if we do that, then we have fy minus fx minus, and then expectation d of g x xi y minus x is greater than equal to 0. I mean, the way these guys are defined is these guys are defined in a normalized form, right? So we have seen this in couple of places as well. So this is like sum of fi 1 to m. So if I compute the expectation of this, and each of these are assumed to be IID, okay, so expectation goes inside, expectation of fi's are all equal because they are IID. So then eventually it's m gets cancelled because m times m of some fi. So basically expectation of any fi is f, right? So this is how we see this. Even if you do it for batches, I will divide by the, I will normalize in a way that I will divide by the size of the batch. Okay, so that shows why expectation of these is fx and fy. Okay, so this is what we were supposed to prove. This now must be the subdifferential. By the definition of the subgradient itself, if I can find an eta that satisfies this inequality, then eta must be the in the subdifferential of f at x. Okay, so this immediately implies, by the definition, this implies that expectation of d g of x xi is in the subdifferential of del f xi at x. Now we will prove the main result, that the stochastic gradient descent is convergent. Okay, so we have done this for gradient descent, we have done this for stochastic gradient descent for various cases like smooth and bounded, strongly convex and bounded. So we have done a variety of proofs. Okay, so let us see if we can prove for stochastic subgradient descent. So we will have the same assumptions. So let assumptions stochastic convex and G bounded subgradients. So these are equivalent of, let's say, ellipsis smoothness that you assumed, okay, ellipsis continuity. So boundedness of the G gradients is similar to saying that it's ellipsis continuous, right? So these are the similar assumptions that we need in this stochastic case as well. And consider the iterates xt generated by the SSD algorithm with the step sizes gamma t greater than 0, then if we look at the average of the solutions that we get, which is defined like this: sum of gamma t xt and t equals 0 to t minus 1 and divided by gamma k equals 0 to t minus 1. I think it's okay. Let us put t. Okay, that's fine. So we will see. So we have this average of the iterates that the SSD algorithm produces, and we will claim that so we have the expectation of T fx bar T minus fx star is bounded by, these are similar results like we did before, x star squared divided by 2 sum of gamma k equals 0 to t minus 1 plus gamma t square g squared and t equals 0 to t minus 1 divided by 2 gamma k and k equals 0 to t minus 1. So these are similar bounds that we have done before, but the only thing is that now we have to make use of these stochastic convex idea. Actually it could be done as an exercise, just the ideas that we have learned are very similar, just we apply similar way. Okay, so let us do this. The proof is not long, so okay, so let us do this proof. So what we will do is that we will start from norm of ht plus 1 minus x star, and we will expand it. So xt plus 1 is coming from the stochastic gradient descent. So we know what is xt plus 1. It is xt minus gamma g xt xi t and so on, right? So we will substitute that here. So this is equal to xt minus x star minus gamma t g of xt xi t norm squared. Okay, and this we will expand this. So if we expand this, then it is xt minus x star whole squared minus 2 xt, we put this other way, usually we do it like that. So gamma t xt xi t xt minus x star plus gamma t squared, and then basically it will be norm of g xt xi t norm squared. So we just expanded this. We have done this many times now, so it's quite familiar now. Now we will use the fact that our gradients are bounded, so the last term will be less than or equal to g. So that's, and we will take expectation as well, but that will come as a next step. Because everywhere we have to take the expectation in the final form also, and the way we get to the f is via the convexity, right? So in the convexity we have fy minus fx minus grad fx y minus x, right? So this will give us fx minus fx star form, okay, which we are looking for there, and this is bounded by g, so this will be less than or equal to g square. But then only thing is that here it will be done in expectation, right? So we have to apply expectation both sides, but we have the definition of expected convexity, right? So the again, like we can, so that exactly gives us that expectation of fx bar minus fx star form. So basically the next steps is applying expectation both sides, and then using the fact that expectation of gradient will be bounded because of the bounded assumptions, and this we will use stochastic convexity. So these are the next steps. So we will take expectation on both sides as a first step. So taking expectation of d both sides, and we will condition it on xt. Yeah. So taking expectation conditioned on xt. So if we do that, then we will have expectation applied here, but not here because it's already conditioned on xt. So no expectation here, but there will be here. So now we are used to all this now. So although it is conditioned on xt, but the gradient is computed on xt in a stochastic way, so hence it remains a stochastic variable. We have seen this before. So this is gamma t, expectation of d of g of xt xi t and xt minus x star, and then the last term is plus gamma t squared, expectation of norm of g xt xi t, and then we will use this two things like less than equal to g square and then stochastic convexity. And the previous result that we have proved is that expectation of the gradients computed, these were the gradients of, so this g, if you look at the g, right, so g was in the subdifferential of f xi t xt, okay, that we know. So remember the approximation of the f, which is f xi t xt, so that we know. And then in the previous result that we proved, then we know that the expectation of this will be in the del f xt. So but if I look at the whole thing, then it is in the del f, not f xi, it's the del f xt. Okay. So what we have here is a quantity which is a subdifferential, which is in the subdifferential of del f xt, and we are given that f is like stochastic convex and so on. So then we will use the convexity as well. So if we use the convexity, then whole thing will be less than equal to norm of xt minus x naught whole squared minus 2 gamma t f xt minus f x star, and then plus gamma t square g square. Okay. So here we have used the fact that f is stochastic convex, and here we have used the fact that the gradients are bounded. So we have this f term on the left hand side. So this is the rearrangement that we will do. So we will take the f on the left hand side, and then everything else on the right hand side, and do some rearrangements to get the answer. So that's a small step. So doing this rearranging, and taking expectation and summing from t equals to 0 t minus 1. So we take the expectation, and then we will sum over all the t's now. Okay, and if we do that, then we get gamma t ed f of xt minus fx star, and this is the expectation computed here, and this is less than equal to expectation norm of xt minus x star minus expectation norm of xt plus 1 minus x star, and this goes with the sum. Okay, so t equals to 0 to t minus 1. So basically this will be a telescopic sum, so many things will get cancelled, something like this we have seen before. And then we had the last term with the gamma g squared, gamma t squared g squared, and t equals to 0 to t minus 1. So by doing this telescopic sum, our goal is to get rid of these t's here, because in the bound you cannot have a something unknown in the bound. Okay, in the bound we always want something which is known, so xt's are not known, so ideally we reduce to x0 or x star. So although x star is also not known, but at least it's some fixed number, we believe, right? So because of the cancellations of these guys and these guys, intermediate terms, only the boundary terms will remain. So that's what we will write as the next step. So this is expectation of norm of x naught minus x star whole squared minus expectation of norm of xt minus x star whole squared, and the last term remains as it is. So this is what the right hand side simplifies to. And then if we look, so what we can do is we can simplify it further. So expectation of this guy will be the same thing, because these are like fixed quantity, these are not really random variable. And we will have, so this is, we don't have an expectation here then. So let us say, yeah, so then in that case it's like this. Okay. So expectation of this term is not required, because none of them are random variable. So this will be just x naught minus x star minus, now this is a minus term of something positive, so I can drop this and still remain greater than equal to. So I make this greater than equal to 0, and I drop this term. Okay, and then this term remains now, plus gamma t squared g squared t equals 0 to t minus 1. Okay, and then we will divide by, because we are looking to prove this for the average, right? So we will divide by the sum of the average term basically. So I will just write down, then you will recall. So in the theorem you will see that the result was for fx bar here, right? So the result was for average. So now we will transform this into average of the iterates, right? The convergence result is for average of the iterates. So if you can recall, sometimes we prove results for average of the iterates, and sometimes we prove results for the last iterate. Okay, so these are the two types of proofs usually we do. Sometimes average iterates is a little bit easier, okay, than the last iterate convergence. So what might happen in average, let us say your solution is here, and you have, your solutions are like that they oscillate around this. Okay, it may happen that the solution is there, and then your x that you are producing at some point they oscillate like this, right? So what might happen is that the average, I mean, if you want to see this as a 1D, it's better, right? So let us say your solution is here, x star, xt on one iteration it was there, and another iteration is there, another iteration is there, let us say another iteration is there, but then it never gets closer. So, and let us say this solution was somewhere like this 0, then I mean it's symmetrical about 0, but it can happen other places as well. So what I'm trying to say is that proving that the average of the iterates converges is sometimes easier than proving that the last iterate is converged, because if I take the average, then oscillations get cancelled and it goes to 0. But if I have to prove the last iterate convergence, last iterate is not converging here, it's oscillating. Okay, so in this case last iterate convergence fails, but average iterate converges. Okay, so usually intuition would be average iterate convergence may be a little bit easier to prove. Okay, in case we have cases like this. So you usually achieving last iterate convergence is considered more interesting. I mean, ideally we don't expect that it will oscillate very frequently, right? So that's why these results we believe are in general it's still useful. Okay, but in case it oscillates, then I mean the last iterate may not converge actually, so one has to be a little bit careful. So we will define this x bar t, the average of the iterates, which is given like gamma t xt, t equals 0 to t minus 1, and divided by gamma k, k equals to 0 to t minus 1. Okay, so we define this x bar t, and for this x bar t, so we will kind of divide it by those constants. I mean, so we will dividing throughout by this guy basically, right? And the sum is already there, gamma t and fxt is already there, and it is being summed over t equals to 0 to t minus 1. So basically what is missing is this this denominator. So if we divide by that, use Jensen's inequality, then I will get here fx bar capital T, right? So we have done this trick before as well, so this is the same trick. Okay, so dividing by 2 sum of gamma k equals 0 to t minus 1, and using Jensen's inequality, so we have expectation of d, then fx bar t, and then minus of fx star is less than equal to, so this is via Jensen, 1 by square root of gamma k equals 0 to t minus 1, summation of gamma t, expectation of d, and then fxt minus fx star, and so what we have done is that we have divided throughout by this term. Okay, so when we divide it throughout by that term, then we have this, and you can try to prove this. Okay, let us start from the left hand side, and so this is expectation of f of this guy, right? So x bar t is sum of gamma t xt, t equals 0 to t minus 1, and divided by sum of gamma k equals 0 to t minus 1. So this is what we have here. We don't really have to look into this. This is a constant, so there is no role here. So basically we have to prove that this is less than or equal to f itself is convex, right? If f is convex, then so these are like the averages of the terms here. So this is like the convex combination of the terms here, right? So if f is convex, then this itself will be less than equal to, and this will come out, okay? And right, and this being a constant, it can further come out, okay? So what do we have here, right? So expectation of t, and then you can write this as f of gamma t divided by sum of gamma k, okay? And then this is the sum, the outer sum, and t equals to 0 to t minus 1, and this is k 0 to t minus 1, and this is xt, okay? So these are like your alpha t, let us say, okay? So this is of the form expectation of t f of alpha, f of the sum of alpha t xt, okay? So this, and these sum to 1, right? So where alpha t is gamma t divided by sum of gamma k, k equal 1 to t minus 1, and sum of alpha t is 1. So hence this is a convex combination. So Jensen's inequality says that this is less than equal to alpha t f of xt, sum of so what will happen now is that these guys kind of come out, right? So gamma t and 1 by this come out of the f, but then they give you less than equal to, okay? So let us do it here. So from Jensen's inequality, so what we have is that so we continue from here, okay? So this will be less than equal to ed, and then this will be alpha t f of sum of f of xt. And this gave us less than equal to. So that's what convex functions mean, right? So f of alpha 1 x1 plus alpha 2 x2 plus alpha n xn alpha 1 x1 plus dot 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 plus alpha n f of xn, right? In general, this is the inequality. And so in our case, alpha t we will substitute back, okay? So in terms of gamma, so ed and alpha t is gamma t divided by gamma k, and then we have f xt and t 1 to t minus 1. And then the term k equal 1 to t minus 1 is like a constant. It has nothing to do because for each t the same sum is there. So this is like a constant, it can come out. So this is ed, and then where is it taken out? It's taken completely way out, okay? So let us do that. Out of the expectation. Expectation is a linear function, so any constant can come completely out. So k equal 1 to t minus 1, expectation of only this guy remains. But then that remains with the sum, right? So we have to put the sum. Now whether you put the sum outside expectation, inside, it doesn't matter. Expectation is a linear function, okay? It can go inside the sum or outside the sum, it doesn't matter. So what we have proved is that this guy is less than equal to this guy, and you can just add this minus f star both sides, so that holds, okay? So we have this now, and what we have is previously we have shown a bound for this, and this is the bound we are going to now substitute here to get the final bound that we had in the theorem, the left hand side this guy, and we left it here until the bound we had, and that's where we will substitute this back, okay? So let us do it here. So with this we have less than equal to, and when we say less than equal to, then this is for this guy now, star. So star is less than equal to, and norm of x naught minus x star whole square divided by 2 gamma k equal 1 to t minus 1 plus gamma t square g square. So basically in the previous where we left, the bounds were up to until here. Now so this guy was less than equal to something, right? So then we divide by this on the both sides of this, and then we have these terms divided by here. So divided by sum of gamma k equals 0 to t minus 1, and here t equals 0 to t minus 1, and there was a 2 also. And this is what we were supposed to prove in the theorem, right? So this is the basic result for stochastic, we call it SSD, okay? Stochastic subgradient descent. Now you can see the forms are very similar. The choices of the step sizes that you will choose will be, it's looking very similar, okay? So for different choices of step size, we will get we can simplify this bound. So this becomes our base result, and based on this they go ahead and do theorem 9.6, some choice of the step size, then they go ahead and they write corollary 9.7, different choice of the step size, then they go ahead and some other step size as well. So that's what they do. We have time. So I can do this choice of step size, right? So we left this as a so we can do this as a last step. So let us choose some step size and see what kind of bound we get, okay? So this is theorem 9.6, and let us say the assumptions of those stochastic convex and all those holds of stochastic convex and G bounded G subgradients, or G bounded subgradients. So G bounded so these two assumptions are as usual, stochastic convex and G bounded subgradient, and we are using the SSD algorithm. So xt is the iterate that is being computed, iterates from SSD algorithm, and then the main thing that we want to study is some choices of the step size. So let us say the choice of the step size we choose is like this, square root of t plus 1, okay, and where gamma is something positive greater than 0. In this case the bound above that we have is reduces to ed f x bar t minus f x star, and this is less than equal to norm of x naught minus x star whole square divided by 4 gamma 1 by square root of t minus 1 plus gamma g square log t divided by 4 square root t minus 1. Okay, so the above bound simplifies to this. I don't know if we can say it's simplified, but this is what we get. So here the integral bounds are used. Okay, so at some point we were trying to prove integral bounds. I will not attempt it again. So I will assume that these integral bounds you can verify as a proof, as an exercise. So we are going to use this integral bound, and with this integral bound, this can be. So the step sizes that we have is gamma t, and this is chosen to be gamma by square root of t plus 1. So basically the step size is decreasing as the iterations of the algorithm are increasing. So eventually it will become 0. So the integral bounds that we are going to use are the follows. So 1 by square root of t plus 1, t equals to 0 to t minus 1. This is greater than equal to s equals 1 to t minus 1, and s plus 1 minus half. So this is a result from analysis you can think of, and this says that this result holds. Okay, and you will get the expressions in t, and here also after integral the expressions will be in t. So but this is the result. Okay, I'm not going to attempt to prove this, but apparently it should be provable. Okay, so this is 2 square root of t minus 1. So this gives us a lower bound. The reason why we are looking at the lower bound is because of these guys, sum of gamma k, right? So in sum of gamma k, if you see, you will have this sum of these 1 by square root t plus 1. So that will be the another integral bound, and the places where you have gamma squared, sum of gamma square here, those we want to upper bound. Okay, so sum of gamma t square, what is the upper bound? So that will be the next I'm going to do, and this will be for sum of gamma t. So sum of gamma t are in the denominator, so I'm looking for a lower bound. Okay, so I'm looking for what is this lower bounded by, so that it can still remain greater than equal. Okay, so this I have to substitute by something lower, and here something upper higher. Okay, so that's why we are looking into this. So this is indeed the lower bound, so we will substitute the denominator sum gamma k by this guy, and now let us look into gamma t square. In that case will be sum of 1 by t, and we want an upper bound there. So so the another integral bound is 1 by t plus 1, t equals 0 to t minus 1 is less than equal to s plus 1 inverse s equals 0 to t minus 1 ds, and this happens to be log t. Okay, so we had an upper bound of the sum of gamma t squared from here, and we have a lower bound on sum of gamma t. So with this the results is immediate now. So plugging this, so we will plug this obviously in the in here. So this is, let us say, double star. So we will plug this in the double star. So then the upper bound that we will get is, and let us write the full thing maybe. So the expected on the left hand side as well. So this is f x bar t minus f x star, and this is bounded by 1 by this guy, right? So x naught minus x star whole square divided by 2, and sum of gamma k is lower bound by this. So this is 2 square root t minus 1, 2 square root of t minus 1, right? And then there is a gamma also here, right? So that gamma will be there. So this will be this sum is this gamma by this. So gamma should be there, right? So there's just gamma should be there. Okay. So in the evening, it's hard to concentrate. So this is just the gamma should be there. And then so this I got from the lower bound, and then I look into the next term, and the next term is gamma t square. Gamma t square is basically gamma square by t plus 1, and the 1 by t plus 1 we have already estimated. So this will be gamma square. So this whole thing will be less than or equal to gamma square log t. So this is gamma square log t. Is everything fine? So yeah, so gamma squared, because of the denominator there is one gamma, so eventually it gets cancelled. So it has been simplified here. So gamma squared log of t divided by the same stuff, right? So it's the same as this. So it's like 4 gamma square root of t minus 1. So this gamma gets cancelled. So now you can compare with what we were supposed to prove, right? So 4 gamma square root t minus 1, and norm of x naught minus x square is there, and gamma g square log t by 4 square root of t minus 1, right? This is where we are supposed to prove. So what are the exercises? Is to verify these two. So exercise 1 is verify these integral bounds. This is calculus stuff, so you have to recall integral bounds. Exercise 2 will be this next corollary that I will leave it as an exercise. So this is corollary 9.7. I will not write this, so you can try to fill these gaps so that we can. So this is a small proof. It's already there. The proof is there. So you can at least understand and write and give it to me, right? So then in the next class we will start with section 9.2, and this will be basically it will take the whole class for the section 9.2, and then we will be left with I think the 10th part is proximal subgradient method. Okay. So basically with this two, meaning I believe maybe I will need 2 more classes to complete this stochastic case, right? So it's good that we see the full scale for the stochastic case, and then we will do for the remaining 6-7 classes we will do the min max problems specifically for the GAN. So that will be the plan. Okay, thank you.